Hello, everyone, and welcome to a new webinar from Optiwave Systems on how to simulate various quantum key distribution algorithms in OptiSystem. My name is Ahmed Atiyah, and today we have a guest from CMC Microsystems, Ahmed Abu Muzwed, and he will join us at the end of the web talking about the presentation, talking about the CMC microsystem and how it can support quantum key distribution and quantum technologies. Okay, so to start this webinar, I'm going to be giving some general information about Optiwave. Then I'm going to give some quantum key distribution background. I'm going to describe the algorithm for BG84. Then I'm showing how implement this algorithm in OptiSystem, in addition of another couple of algorithms. Then I'll show you some results and discussions, and we conclude. Then open up for questions. As you know, Optiwave developed innovative software tools to users, allowing them designing, simulating, and optimizing different components, linked systems, and networks. Optiwave software offers users a distinctive competitive advantage using the software packages to shorten product time introduction to market and to improve the product quality through simulation and investigating of the system before building it, as well as enhancing product cost effectiveness and avoiding any unexpected results without this simulation. Optiwave offers different software packages. We offer these packages in a system-level package, which include OptiSystem software and OptiSpice software, which is an optoelectronics software, can be used for designing photonic integrated circuits as well as any optoelectronic circuits. There is a component-level package which includes mode solver software, which is like OptiMode software or OptiFDDT software, as well as beam propagation method software, designing gratings with OptiGrating and designing fibers with OptiFiber. And another software package, which is instrumentation level, it's called OptiInstrument, and this software enables users to communicate with instruments and control the instrument remotely and collect data from it and process this data, use this data as well in OptiSystem software. Now, users can download neat software packages from our website located at optiwave.com, and you can download 30 days trial of any software. Once you click on the 30 days evaluation, you should be able to fill up the registration on our website, and then after you register, you can download any package, and these packages can be located at program files on the C drive and then Optiwave software. OptiSystem software has many components, or 600 components, which addresses most of the components, devices, and equipment to build your system and analyze it and work with it for any design you like to. This includes sources, which includes CW continuous wave lasers, LEDs, VCSELs, DFB lasers, Fabry Bureau, white light sources. There's different types of modulators, Mach-Zehnder modulators with single drive or dual drive, single port or dual ports, and different electro-absorption modulators, as well as phase modulators, amplitude modulators, frequency modulators. There is different types of bit sequence generators. So there is random, pseudo-random bit sequence generator, there is user-defined sequence, and there is compliance test patterns generators. Optical fibers, we offer single-mode fiber models, multi-mode fiber models, multi-core fiber models as well. Electrical modulators, you can do off-DM quadrature modulators. We support in OptiSystem almost all the modulation formats like return to zero, non-return to zero, carrier suppressed, return to zero, dual binary, differential phase shift keying. any type of order of phase shift keying, any order of QAM, any order of PAM, pulse position modulation, and probabilistic amplitude shaping. Filters, we offer optical filters, electrical filters, which includes also FPGs for filtering as well as for compensation of dispersion. There is electro-optic circuits, which is we have OptiSpice software can be used within OptiSystem, so you can design ring resonators and you have laser drivers and use them in OptiSystem, as well as you can have switches, different type of switches, optical, electrical switches, and interconnect. For signal processing, we offer a wide range of signal processing components from DSP to equalizers, electronics with different types of equalizers, as well as data recoveries and clock recovery and 3-hour generators. For FIC, we have Reed-Solomon algorithms, low density parity checks algorithm, as well as different mapping schemes. We do mapping from 4-bit to 55 bits, 8 bits to 10 bits, and so on. Detectors, we offer detectors, APD, SPD, single photon detector, which is, we're going to talk about it today for this webinar on quantum key distribution. Optical amplifiers, we have almost all the materials, fibers, which you can use to build your own amplifier, or you can have a block of optical amplifiers, as well as semiconductor amplifiers, Raman amplifiers, and waveguide amplifiers. Electric amplifiers, we do transimpedance amplifier, linear and non-linear, and as well as limiting amplifier and automatic gain control amplifier. Passive modules, you have almost everything you need for building your system, from couplers, muxes, arrayed waveguides, switches, attenuators, circulators, isolators, and so on. For multi-mode applications, we have models for multi-mode fibers, multi-mode amplifiers, as well as visualizers to see the modes and passive devices to support the multi-mode application. In optical channel, we offer the fiber, as you saw, as well as satellite channels, Li-Fi channels, a free space optic channel, and visible light communication, as well as underwater free space optics. And visualizers, we offer a wide range of visualizers to enable users to monitor signals in the optical domain or electrical domain, binary domain, or memory, as well as we offer equipment, test equipment like PERT, light wave analyzers. The software of the system allow users to do the simulation in both directions, in unidirection or bidirection, and also using single polarization or dual polarization. So you have a comprehensive software here to allow users to design their application. In the applications, we have a wide range of examples, over 1,000 examples, and they are categorized in different categories. You can access them on the example library usually when you download the software. And as you can see here, they are categorized based on the application. So you have application for advanced modulation, for radio front haul, for 5G applications. There is optical amplifiers application, lasers, microwave photonics, sensors, wireless communication channels, as well as spatial division multiplexing for few modes or multi-modes, or you can have multi-core fiber single mode or multi-core fibers with multi-mode. So we support the quantum key distribution, which is the topic of today's webinar. Now, OptiSystem also has a unique feature, which is allow users to communicate with other software packages in Optiwave offering, which is OptiGrating and OptiBVM, OptiSpice, as well as OptiInstrument. Also externally, we can support communication with MATLAB, with Python, with C++, as well as Scilab. So users can actually write their own codes and use them within the software, OptiSystem software, or they can call OptiSystem from these packages. Like you can call OptiSystem from Python or from MATLAB, and then you run OptiSystem, and then you get the results of OptiSystem, and then continue in the software package you have. As I mentioned, we have over 600 components in the different visualizers, as well as over 1,000 examples in OptiSystem. Okay, Now going after this introduction about Optiwave product and OptiSystem mainly, we're going to move into the quantum key distribution and background of it. So just here, we're going to distinguish between the bits and qubits. So typically with digital computers, we use classic bits, which is either ones or zeros. And these ones and zeros can be turning off the laser on and off, presence of the signal or absence of the signal. On the other hand, if you use quantum computers, you can use qubits, and these qubits can be either 1 or 0, or can have two distinct states that can be also exist in superposition and entangled with each other qubit. Types of qubits can be spin. So most of the particles behave like a magnet where you can spin orientation up or down. So up or down, their orientation of spinning. And also trapped atoms and ions can have different energy levels to have ground states or excited state, a higher energy level. Or you can have like photons with polarization control, which is mainly used in this analysis in OptiSystem for today's webinar. We're going to concentrate on polarization states. And then you can have also control the path of the photons can take for using some components or the time of arrivals of photons. There is also superconducting circuits where the direction of current flow will determine these kind of qubits. Application and fields for quantum, so you can have quantum sensing, quantum computing, quantum communication as a field of interest. As well, application, you can have different applications for including high efficiency storage batteries, cybersecurity, drug development, banking, and financial institutions. Okay, now here I'm just going to give some general information about quantum key distribution and how to be used in practice. Typically, you have quantum key generated, usually generated every few days and shared between users. We don't use quantum key distribution with some algorithms, especially when single photon we are using because of the noise of this EDFA, so it's going to block these photons. In quantum key distribution also, usually you have one key per customer on a single fiber, especially in the access network, and can combine this quantum key distribution or keys and share them on the same fiber in the core. Different types of filters can be used, spatial, temporal, or spectral filters to eliminate the noise coming from the sunlight, especially with free space quantum communication. And when you do, for example, satellite quantum transmission or communication, memory components are a key for quantum memory is a component which is to overcome the latencies issues. Challenge is to transmit the data and quantum key over the same fiber. This is something which is lots of people are looking into resolving this issue. Quantum key protocols, like quantum key distribution, is a collection of protocols or schemes used to provide keys between two parties, usually known as Alice and Bob, and they are based on quantum physics and quantum mechanics. The general quantum key protocols in the literature you can find, this is the first protocol, which is called P84 and related to the inventors of this protocol, Bennett and Prasad. And there is other algorithms called decoy, quantum key distribution. There is coherent one-way algorithm, continuous variable P892, continuous variable quantum key using GG algorithm, which is Gross, Hans, and Geringer 02 coherent protocols. There is other algorithms called sending or not twin field quantum key distribution and discrete variable distribution. So mainly they are divided, these algorithms, into either discrete variable or continuous variable. And the discrete variable you send a single photon, continuous variable you send a stream of photons. And typically in communication, they rather people to use continuous if possible, because this is easier and to implement. In OptiSystem, we offer many components and visualizers to allow users to work with the quantum key distribution. and this include a select and a switch devices. And these devices basically have built-in capability to allow the user to randomly select any of these ports into the output port, or transmit what is coming into the input port for the switch into one of these ports. A replacement for this component, you can have another type of select and switch, which these two components, you can put your random sequence here or user-defined sequence if you like, and then you can select these ports at the output of the select switch randomly based on what the bit coming, and also you can do that on the opposite way. You can get an output here based on what is the input sequence. So if you have 2 ports, you can use 0 and 1. If you have multi-ports, let's say 4 ports, you can use combination of bits like 0, 1, 2 bits basically to allow the selection of these ports. Now, other components is you can use bin detectors. There is white light sources. There is noise sources to do analysis, to add up into the system for analysis. You have binary sequence visualizers. We add up features into these ones to count the coming ones and zeros and compare between the ports how many ones are matching. And this is very important when you try to match between Alice and Bob sequences. There is eye visualizers, it's data recovery, and also we have a new visualizer, we call it Pulse Polarization Meter, where you can look at the polarization state of every pulse. Like when you send a stream of pulses, and each pulse represents, let's say, a photon or a stream of photons, then you can send in each pulse a separate polarization state. Okay, so you can detect that on this visualizer, which is Pulses Polarization Meter. Okay, now one of the important components, as I mentioned in quantum, is the single photon pulse generator. And this is based on, you have a stream of pulses, and each pulses you need to control how many photons you need in them. So if you wanted to follow up the algorithm, so you have the average power of this sequence is going to be depends on the bit, if it's 1 or 0, and then the peak power, and then the pulse width at half maximum. This is typically for NRZ. And then based on the energy and the relationship with average power, you can find the relation with the number of photons, and then you can get the number of photons related to the average power. Using that, we created the single pulse photon pulsed laser. And with that, users will be able to set up the number of photons they want at the output port. And the component, basically what happens is it has an internal attenuator. It calculates the average power. It calculates how much attenuation I need to be able to get a single photon at the output of the device. Okay, so now we're going to move into the different protocols we're going to look into in this webinar. We can look into the BP84, the B92, and the coherent one-way algorithm. In this slide here, trying to describe what is the BP84 how it works. So you have, as I mentioned, 2 parties, is the Alice and Bob. And what's happened is the first step is Alice send different phases, different states of polarization of photons, and can be circular left or rectilinear, vertical or horizontal, or circular right. So it's sent randomly all of these states. Now, what's the second step is Bob will receive them, okay? And then he measures the bases. So he measured, like, for example, he get these bases at the receiver side, because what's happened is the transmitted photons will be affected with the channel. It's going to be affected also with the eavesdropper, okay? So these two factors affect the reception of these states. So he will basically detect the bases in his second step. So he will say, I'm here rectilinear, I'm here circular, and so on. Now, the third step here is, as you can see, some of these photons are missing because it could be lost or could be not received at all, okay? Now, the next step is Bob will tell Alice which bases he detects. So he will tell her, I detect this base is the first one. So there would be a communication using a regular channel. And this channel would tell Bob will tell Alice that I receive here rectilinear, I received here circular, and so on. Now, the next step is the scaling step, which is Alice will tell Bob which of these spaces are correct. So this space is correct because she sent circular, but as you can see here, it doesn't tell him if it is circular right or circular left, but tell him is these spaces are correct, okay? So that adds an additional error could be happening because after Alice tells Bob what are the bases correct, is the next step is going to be coding of this Bob detected state. So he will detect here basically uh, circular right or so on, and then after that we'll convert it into bits, ones and zeros, depends on if it is horizontal or vertical. And then after that, the transmission is going to be established. And this is the key will be established between Bob and Alice. Okay. So the other algorithm which I'm going to show you today in OptiSystem is the coherent one-way. And this coherent one-way is you have more than one photon transmitted. So you have pulses, and these pulses are coded with a decoy pulse. And what's happened is within you have a repetition rate, and within the bit period you send two pulses. If it is a bit, if it is bit one, you send. If it is bit, you send an attenuated pulse, and then followed by another full pulse within, like the width of these pulses is half of the bit period. Okay, so within a bit period, let's say the bit rate is 1 gigabit per second, then the bit period is 1 nanosecond. So within 0.5 nanosecond, you send an attenuated pulse and followed by a full pulse here for bit one, and full pulse within the half bit period for the first part, and the second part you send a attenuated pulse for the bit zero. And then after that, you can transmit this, and then at the Bob side, you can detect it using different detectors and then decide what you send. So these two schemes here, as you can see, we build them in OptiSystem. So I'm going to go now into OptiSystem to show you the different schemes. So let me go here into OptiSystem. Okay, so this is the setup for the cow algorithm. As you can see here, there is the different section. So this section is for generating the 1 bit stream, and this is for generating the 0 bit stream, and this is the section where generate the decoy state. And as you can see here, there is different components used is logic binary, AND gates, and inverters, as well as the optical components. As you can see here, I run these projects ahead of time, just only to make sure that avoid the delay in the calculation. But as you can see here, if you look at the pulses, this is here, you can see the pulses. This is the attenuated pulses, and this is the full pulse within the bit period. It depends on what you send in here. So you see 0, 1, and so on. You can follow up the structure. And the other one here, you can see this is the 1, and this is bit 0 in principle. And this is the decoy pulses. You can see the pulses, how they send it, the decoy pulses. Okay, and then after that, you have the detection scheme. You have the two detectors, and you can decide the errors, the quantum bit error rate after that. Okay, so let's go to the, let me, sorry, get it to go here. Okay. So this is the decoy, the count implementation in OptiSystem. The other one is the implementation of BB84. So in BB84, I'm going to show you here the different sections and the transmission over a free space optical channel, how you can do it. Basically, as you can see in this section, you have a laser diode, CW laser, and then you have attenuator, where you can set up, depends on the bit rate of the user. So let me go actually directly into OptiSystem here. So let me minimize this one, and okay, so okay, so this is the BB84. Okay, So this layout here, I have, as you can see here, many layouts which is used for this analysis. This is the Alice setup. So Alice setup has a CW laser and then attenuator to control the power level which is going through and how many photons you need to have. And then you have a switch here. So the switch, if you go to the switch here, double click on it and go to the data sheet, you can the switch how it works. If you have bit 0 coming up, you select the upper port. If you bit 1 comes up, you select the lower port. So this is what's happening with the switch. So you can get a stream of bits arbitrarily here. So Alice is choosing randomly the bases. So the bases could be a rectilinear or could be a circular. So this is the first step. So either choose this one or choose this one. And the next step is randomly choosing also rectilinear horizontal or rectilinear vertical. So this component here, as you can see, if double click, it's the linear polarizer. And you can control the angle here. If it is 0, it's horizontal. If it's 90 degrees, is the vertical. You can set it up the vertical. And then after the selection of this path or this path is going to be depending on what is the bits is coming here. So as you can see here, if you look at the signal on this part, on the signal or this part is going to be the CW light is going to be, as you can see here, switch on and off depends on the sequence here. And then after that, the pulses is going to be selected randomly again, this option or that option. Now, after this stage, what's happened after this selection of these states and bases, you combine them and then you are ready to go to transmit them over the channel. So this is what is the basically Alice setup. And after here Alice setup, as you can see on this part here, because you are adding pulses and without any modulation or anything, is you're going to have a continuous light here, which is the CW light, as you can see here. Okay, so this one here, the output is just comparing what is coming at this port and what is coming at the output of port. So here you have pulses because you can turn on and off the switch. But on this part here, you're combining all these pulses, which you end up as with the CW light, but it's switched on with different polarization. So each bit period, you have a different state of polarization. Now, the other part here, which is the Bob setup. So Bob is going to receive a signal, as you can see from here. And then he, as we mentioned in the algorithm, is going to choose the bases. So he's going to choose this base or this base randomly within this sequence. Okay, so he chooses this one or just one randomly. And the second step is going to be choosing which one of these states of, if it is choosing rectilinear or circular, also randomly. Now, the comparison between what Alice sent and what Bob bases sent is going to be, we're going to take this state here, and then we can do XOR on them until to control what we are analyzing in the end of the day. But after that, as you can see here, you take the state, you detect it, you do data recovery, and then after that, you can do a QBR analysis. On the Eve, now this is the Eve section. Eve section is the eavesdropper. The eavesdropper, typically what he can do, he can receive on the channel during the transmission. You can, for example, tap the signal and then can alter the state of polarization of these things. So you have different options here. You can have either delay or phase delay. So any distortion can be happening, changing the polarization state, or what is the basis or the state sent by Alice could go through to Bob, or also the eavesdropper could completely send in new states and new bases randomly, as you can see here. So there is 4 or 3 possibilities: altering or allowing the qubit to go through, or generating a new qubit. And the 4th option is doing nothing, is here sending nothing, basically. Is like blank bit at that, or qubit at that part. And after that, it's going to go continue on the channel and goes to Bob. So this is kind of the structures. Now, any of these components, you can search for them. You put your mouse in the component here. As you can see, this is the default component library, where you have almost, as we said, over actually 600 components, and they are categorized. You can, if you need to search for any component, just put your mouse here, find component, and enter the component name, and you can basically do the search for the component and find it in its proper location in the library here. Okay. The issue of if you want to see more information about how to build the system and all of that, there is some webinars on our YouTube channel or our website. You can take a look at there, and then it shows you the basics of how building the system and so on. Okay, so next step here, as you can see, what we do is we have 4 options here for transmission. So the what is Alice is generating here, we're gonna transmit it back to back to Bob without any interference from Eve, or we can transmit it over a free space optic channel without any interference from Eve, or the other options is Eve interfering with the back-to-back transmission and Eve interfering with free space optic channel. And so we have 4 options here in the analysis. So I'm going to go just quickly first into the slides just to follow up on them and show you what is going on, and then I demonstrate it in OptiSystem. Okay, so let me go here actually out. Okay, so this is what we discussed, the different options of the analysis. Okay, now here in the process here, just to summarize what is the capabilities of the OptiSystem for quantum key distribution. You can create a single photon laser. You can have add bits matching analysis in the dual binary analyzer, allow controlling selected switch. So this is a summary of what I talked about these different components in OptiSystem. And this is the pulses polarization meter, and this is the component. Okay, so as I mentioned to you here, this is the simulation setup. Okay, and this is the process of, again, this is very important, is the process of comparing the bases of Bob with what is Alice sent is done through an XOR gate. And the reason for that, whenever you have similarity, you're going to get a bit 1. When you have any differences between the 2 states, you're going to get 0. So what happened is we use these bits here to control the next stage of Bob's decision to consider that bit with the qubits or not, a bit period with the qubits or not. So this is how we control the process of selection of or ignoring that specific bit period. Okay. Now in the example here, we used 128 bits sequence at 1 gigabit per second data rate. Okay. Now this is the full setup. Okay, so showing you the Alice part and showing you the Bob part, and as you can see here, the transmission and reception for Bob is done back to back. So this is the first analysis, which I'm going to show it to you in OptiSystem in a few minutes. Okay, and then the second part here is the back to back, but no Eve. Okay, so now this is the decision circuitry here at the XNOR. The XNOR. You can see what's happened is the choice of the bases, which is happened here. Choice of the bases by Alice is passed to this XNOR, and the choice of the bases of Bob is also passed here. And this, whenever we have one, it's going to be selected and controlling this switch to be considered or not considered in the calculation. Okay, so or ignored. Okay, so this is how we control the comparison in the algorithm. Okay, now this is the results of the I diagrams or qubits qubits error rate even with back-to-back. As you can see, this is clean I. And also here we have put the pulse polarization meter. And the pulse polarization meter, the advantage of it, as you can see, it shows you the state of polarization for every. So whenever we have 0, 0, 0, it means a bit is ignored. And if you have a state of polarization, as you can see here, -1 circular polarization or 1, it's going to give you the linear polarization and so on. So you can also use that for analysis and calculating if you want manually or externally using another process to analyze the quantum QBR. This part here is the, in addition to the back-to-back, so you have the LS transmitting the qubits and Eve doing one of these options randomly, so either altering or either passing or either sending a new qubits or doing the null, and then goes to Bob, and then Bob detect, and then analysis here is happening. What's happened here, you're going to see there is different levels appearing because of Eve, because Eve is doing alteration and sending another qubit state. So there is a lot of lots of errors here, and that's where you see the QBR is going down to about maybe 0.003 the bit error rate or QBR. Now, once we start doing the free space transmission, you can do this kind of key transmission over any type of channel in OptiSystem. So you can do it over fiber, which is wired, or single mode or multi-mode. You can do it over in air using the free space optic channel, or underwater. If you wanted to do it, you can have underwater. There's different channel for underwater, line of sight under channel, which means direct path, or non-line of sight, which means reflection from the surface of water to the receiver. So different options you can do. In this example here, or in this analysis, we did the simulation using the free space optic channel. We used 0.2 kilometers. We swept that up to 500 meters in this example. And the attenuation is like clear sky. You can play around with the weather conditions, so you can have any type of weather you wanted to have. And then also you can control the telescopes, transmitter telescopes, and receiver telescope, and so on. Now, adding up the free space optic channel between Alice and between Bob, as you can see here, there is two options we have, with Eve or without Eve. So this without Eve, you can have errors here because of the channel conditions. So you can have it's still very clean eye, and but the error instead of 0 start to get higher. So it depends on the channel. If you want to put more attenuation, longer range, different conditions, this is we're gonna close up. But the idea here is without Eve, you don't have any distortion, you have no interference, okay? And then once you have Eve into the picture with all options as mentioned before, 4 of them, then how you build it, you can go some part here with the free space optic channel, and then Eve comes up, and then you continue with the free space optic channel, another section here. Okay, now you start to get also the interferences because of the states, and the error as well increased in this section. Okay, so here is the eyes for the different situations we described. Okay, now I'm gonna go the final algorithm I'm gonna describe here is the algorithm where you have with beam polarization beam splitter, and you have the section of Alice is almost the same. You have different bases and different states. You can transmit over the channel, and then here what you have is you have a beam splitter, and you can set up its angle at 0 degree or 45 degrees. And with 2 diodes, you should be able to detect if the basis is correct and if the state is correct, as we can show you here in the, this is some of the analysis done. So if you can see here, for example, if the beam polarization beam splitter state is 0, and then whatever you send at the Alice side, if it's 0, detector 1 is going to be on the top side lit, and detector 2 is off. However, if you do receive an opposite state, okay, so the other LED here, is going to be lit. Now, if you have 0 or 90 degrees on the beam splitter, and you send circular polarization, both LEDs would going to be lit. That's the good thing about this method here. You can have 2 sections, one section for detecting the linear polarization, vertical or horizontal, and the other one section for detecting the circular polarization. So when you set up the polarization beam splitter at 45 degrees and you send 45 degrees polarization, now it's opposite what's happening here. You have the bottom LED or detector is going to detect the polarization, and if it is 135, it's the upper one light. However, if you put linear on them, both of them is going to lit. Okay, so that's the kind of algorithm which can be used. And here is some analysis. Go. I'm adding up some references here in this presentation, but let me, before I finalize and move, give the podium here to Ahmed from CMC to talk about their capabilities. I'll just show quickly the example built up of the other example here. So you can see here, this is the setup. It starts from sequences here, which is random sequence. So you can have, and this component we use the select. The select have, as I mentioned to you, if you go to the component property here, okay, so component properties here, you can have control number of ports. You can have, if you like, sweep it, and then you can control your randomness internally or externally, actually. And then the selection of this light onto one of these states, you can put a polarization on it. You can transmit it, and then here you can see the two stages. This LED or this LED or this pin detector depends on the polarization angle. You can set it, if it is 0, you can detect on this section everything. One of these LED will be LED if you have the same polarization, but if 2 of them, it means you send opposite, which means circular. On this section, if both of them LED, it means you send linear. And as you can see here, we have 45 degrees. So either the top one or bottom one will LED, depends on the if it's 45 degrees or 135, right circular or left circular, it transmitted. So with this, I'm gonna now go here into the last section here, where I'm gonna move into and give the podium to Ahmed, and he's gonna talk about CMC. So go ahead, please, Ahmed.
Thank you, Ahmed, for the opportunity. I'm gonna share my screen. Is that no? And then okay, you see my screen and hear me well, Ahmed?
Yes, everything is
okay,
good.
Great. Okay. Thanks, everyone. Thanks, Optiwave team, for providing me the opportunity to speak here. I'm gonna talk about CMC Microsystem services, in particular, our services in quantum technologies. So first, I'd like to give a brief overview about CMC. CMC Microsystem is a not-for-profit corporation that's almost 40 years old, serving more than 10,000 academic and industry participants. CMC has 5 technical teams to provide services and simplify access to reduced cost to advanced technologies, including microelectronics, photonics, IoT, MEMS, and quantum technologies. So today I'm going to highlight only the photonics and quantum, but we have other services as well for other technologies. CMC manages the collaboration between almost 70 universities and colleges in Canada, connecting 10,000 academic members and 1,200 companies to design, build, and test prototypes in advanced technologies. This slide here shows the outcomes, including 785 trained HQP landing jobs in industry, and also the creation of new startup companies. This slide also shows the numbers across the provinces of Canada. CMC has served 67 academic institutions in Canada, 37 institutions in the US, 7 other institutions, 64 companies, and 9 other organizations, as shown in this map. Over almost 40 years, CMC has built a solid supply chain for advanced technologies, over 100 alliances in 17 countries, as shown in this map. CMC is supporting building the Canadian capability by creating a national supply chain of over 50 organizations. So as you can see here on the slide, we show only one examples under 3 categories: CAD, Fab, and Lab. As I mentioned earlier, CMC has built the supply chain to advanced technologies across 17 countries, but also CMC convenes international peer organizations annually to exchange insights and collaborate on projects to introduce a new technology offering to our members. So we streamline our services under 3 categories: CAD, Fab, and Lab. Under CAD, we enable access to many CAD tools, including Optiwave tools. Users could use their computers or use our secure distributed private cloud. Also, if you are a member or would like to become a member of the Virtual Environment Incubator, that's we call it VI. It's specifically for startup companies. You can contact us to enable access to Optiwave tools and other tools and benefits for startup companies. Under Fab, we have access to many foundries at reduced cost, as I mentioned, and that's actually backed by engineering support for first-time right designs. We could help with the design for test, design for packaging, and also we offer packaging and assembly services. Here's an example of some of the foundries that we can have access to. For photonics, you can check the schedule on our website. We have access to Advanced Microfoundry in Singapore, Global Foundries, and Applied Nanotools for fast prototyping in Canada. We have also foundries for superconducting devices. This slide shows the 3-year highlights for the designs prototyped. As you can see here that we have more than 1,200 designs fabricated over the 3 years. Quantum was introduced in the year of 2021, 2022, with only 7 designs. That number was more than doubled in less than 2 years. So there is an interest and progress in the quantum technologies in Canada. We also have many services under lab. So the goal here is to speed your research and development and help SMEs bringing their products faster to market. We also offer technical contract services, including quantum coding, quantum and photonic design, helping startups with the design and prototyping processes. So if you want to have your help with the design, you could actually, we can offer contract work. This brings me to the quantum services. As I mentioned, we have dedicated team working on the bridging the quantum science to quantum technology, including the quantum computing, quantum communications, and also quantum sensing. So we span all the applications. The quantum team can support you access IBM Quantum Hub, Xanadu Quantum Sandbox, and IonQ via Google Cloud. All this is backed by engineering support. So we can actually support you if you need quantum computing for finance, security, or any other application. As part of the quantum services, as I mentioned, we have MPW fabrication services targeting quantum devices, including PDK development for superconducting devices and quantum photonics. The example here shows a quantum qubit based on a superconducting device. We also have access to quantum photonics. For example, in Canada, we have access to applied nanotools for the rapid prototyping and silicon or silicon nitride platforms that can be actually used to build your quantum photonic devices. CMC Microsystems also runs Basecamp training programs comprising many courses in almost every technology area. These courses introduce engineers and scientists to advanced technologies, providing a unique combination of theory and lab work through the design, fabrication, test cycle. So designers can also fabricate their chips. For photonics and quantum photonics, we have the SciEpic passive and active silicon photonics workshop, and also the quantum workshop in collaboration with NCR Crete, British Columbia. So this year, the quantum photonics workshop was a big success. It was aligned with Photonics North. The workshop starts with theoretical background applications of silicon photonics, component simulation, implementation, and design for fabrication. Of course, participants can submit their designs for fabrication at Applied Nanotools, and after they get their chips back, they can test them or arrange for testing at another facility. We can help actually connect you with the right facility. So in general, we have over 240 HQP trained from CMC Quantum Basecamp, including the QSite Quantum BC workshop, Silicon Photonics workshop, and also there's another workshop, Build Your Own Superconducting Device, which was the world's first to teach how to design, simulate, and test quantum superconducting quantum devices. So as you can see here, we target many hardware, not only photonics. Considering building the quantum capabilities in Canada, I would like to speak about the Fabric proposal led by CMC and 13 other founding organizations. The aim here is to build the Canadian ecosystem and accelerate the development of the made in Canada microchip manufacturing process, internet-connected products, and also quantum technologies. For building the capability in Canada, manufacturers enhance or develop new processes in MEMS, photonics, compound semiconductors, and of course, quantum and superconducting technologies, accelerate R&D of IoT products and services by SMEs operating in all verticals, develop skills needed by industry, and another goal is to take the quantum technologies to market by enabling SMEs and academics to access quantum technologies and accelerate their adoption in Canada. Of course, we need to grow Canada's semiconductor ecosystem by leveraging each other's strengths, developing ecosystem IP, and probably attracting investment. Also, the development of cohesive Canadian supply chains in core technologies for rapid prototyping and low and medium volume production in Canada. For more information, please check the link on this slide. I hope I gave you a comprehensive overview of our services, in particular the quantum services. We can work together to lower barriers to technology adoption for the quantum technology and other applications. Thank you for the attention. Please reach out to me if you would like to get more information about the membership or any opportunities to work together. Please don't hesitate to contact me. Thanks again for your attention. Thanks, Ahmed.
Thanks, Ahmed, for the introduction about CMC and the importance for quantum support. So let me share the last screen here. So,
okay, thanks.
Okay, let me go into this mode. Okay, so what we have here next is just concluding the presentation. In this presentation, what we did is presenting PP84 quantum key demonstrated using OptiSystem software with the COW software model as well. We did transmit the quantum data over free space optical channel, and then we used 1 gigabit modulated data, or not modulated, it's actually the data rate at transmitted over a free space optical channel 500 meter with a channel loss 0.5 dB. And we use the polarization pulse meter as well as the analysis using LEDs to analyze the states of detected quantum qubit. If you have any question or any support question, please don't hesitate to contact me at ahmed.atiyah@optiwave.com or send an email to support@optiwave.com. With this, we go to the question and answer section. So we have about 7 minutes. Let's start with that. So I'm going to stop sharing and then move into the question section. Okay, so there is a few questions here. Start from the top. Can OptiSystem be used for other schemes not described in your presentation? So let me answer this one. Is OptiSystem software, as I mentioned, there's about 600 components, over 600 components and visualizers which can be used to build this system. Now, if there is a missing component and you want to kind of build your system around it, you can use the Python codes or in the Python component or MATLAB code in the MATLAB component and integrate that specific algorithm in the software. So in general, my quick answer is definitely you should be able to simulate any scheme in OptiSystem. Another question here, is it possible to use EDFA to amplify quantum key using the BP84 algorithm? So in the BP84 algorithm, typically you send a single photon on the channel, and then single photon is going to be problematic to because of very low power levels of these pulses you send them with this single photon. So you're going to be overwhelmed with the noise and you will not be able to detect this state of polarization of any of these photons. So even in the single photon detector, you have to minimize the noise as much as possible to avoid the the noise basically. So the thermal noise is very limiting, and as well as shot noise. So these things you have to pay attention when you use these components in OptiSystem. Okay, another question here is single photon counting module available as a module in the software? The single photon detector, it is a new component we introduced in 21.1 version of OptiSystem. So older versions doesn't have it. As I mentioned, you can download the 30 days trial version and you can take a look at it. We actually, at this moment, we are adding up new features into the single photon detector where the user would be able to kind of generate a TTL signal or pulses whenever the photon is present at the receiver. And we take into account parameters like the time zones and so on. Another question here. How is the dead time of the SPD work? So the SPD basically, typically what happens is you're going to detect a photon. When a photon is detected at the receiver, there is a time for the photon to get recovered and be able to detect another photon. And this time depends on the technology of the detector. And let's say, for example, if the dead time is 20 nanosecond and your photon coming before that, so you will not be able to detect a photon within this time frame. Can we have access to other technologies such as thin film lithium niobate? I think, Ahmed, this question is for you.
Okay, yeah. Actually, CMC is considering introduction of new technology. So if you're interested, in thin film lithium niobate, it's on our radar, right? But if you have users in Canada, right, definitely we can introduce it. Not only thin film lithium niobate, any other technology, low-loss silicon nitride, any other technology that you're interested in, just contact us. We can introduce it together. Yeah, thanks.
Okay, thank you, Ahmed. Okay, another question is, may we use the components of quantum key distribution in version 16 of OptiSystem? So OptiSystem version 16 does not have the SPD or single photon detector or single photon or pulsed laser. Only version 21 has them. If you need, you can upgrade your software package and to have this. Please contact us at support@info@optiwave.com. Also, we can communicate with you to show you how to update. Kindly upload the recording of this webinar on Optiwave website. So yeah, after this meeting, the recording is going to be available at our YouTube channel, and will be sent to a link for all registered users, basically. What is the difference between accessing MBW runs through CMC and directly to the founder? Yeah, Matt, this is a question for you.
Okay, yeah. So if you become a member, CMC, it's not only the MPW run, it's the engineering support, design for manufacturing, design for, packaging, and also we offer, lower price, like the cost is going to be lower, right? And we also offer you the support for your devices, yeah.
Okay, thanks. Question here about sensing. Regarding the sensing application, vibration sensing perspective, are there any advantage to use quantum key distribution? Is there any advantage in use noise elimination? Okay, so in quantum sensing is a very hot topic actually right now, is to kind of minimize the noise and improve the sensitivity of your system. So at this moment, quantum key distribution is the purpose of it is to establish communication between two parties, and it's different than the sensing application. However, Optiwave is collaborating with a few universities to work on quantum sensing, and hopefully in the next couple of years we will have solutions for quantum sensing. The other question is for CMC. Is there any possibility of simulating relay scatter in the labs for vibration sensing application? I'm not sure, Ahmed, if you have any answer to this.
Yeah, just contact us if you need any specific, because we need to know the details. And of course, we can connect you with the right case if it's available in Canada or elsewhere. We have our collaborators probably. Contact me. Yeah.
Okay, thanks. Okay, the question here, can OptiSystem calculate quantum error rate? The quantum error rate, a quantum bit error rate is similar to the bit error rate in regular communication. So as you saw in the diagram I showed you, the bits is going to be, or the base is going to be selected or ignored. So if you look at actually the eye, you're going to see lots of zeros in the eye and a little bit number of ones in there, which means the calculated bit error rate is actually the QBER, which is generated in the system. Is the only reason for errors what Eve does, or there is noises in the channel that would cause the eye opening to shrink? Is actually both. So Eve is causing alteration of the eye. So the different levels is coming from Eve, as well as the eyes can close mostly because of the channel. Okay, so the noises in the channel, noises in the detector as well, and the system. So it's both. Okay, so lots of questions coming up here. Can you use vertical, horizontal, and diagonal, anti-diagonal instead of zero? Okay, so the diagonal, is typically, if you put the diagonal at 45 degrees, is like circular, right? So, but if you do diagonal at a different angle, then it becomes elliptical polarization. So this is something could be investigated using the setup and take a look at it. Please also provide links where a detailed tutorial of OptiSystem. Okay, so if you have any, if you have this question about the tutorials, Optiwave website is having lots of videos, tutorials, and white papers on the different software packages. So you might search on it, and if you need more help, please just send an email to support or to my email here, and then we can help you on that part. Okay. Is it possible to plot 2D and 3D graphs with OptiSystem? If so, how? Okay. Let me go here just quickly, just to go, and then maybe we conclude the webinar with it because of the time. If you look at the OptiSystem here, as you can see, there is a report page here under, and the report page here allows you to plot 2D graphs as well as plot 3D graphs, and you can also have grid and text messages. So you have lots of flexibility here, and you can import all of this information basically into your. I didn't share screen actually. Let me share screen. Sorry for that. If I go here into OptiSystem, in OptiSystem in the layout, this is your layout where you design your project, and there is a report page here. And in the report page here, you have different. Let me delete these ones. You have different possibility to have 2D graph or 3D graph, as you see here, and you can plot the control what is the signal on each axis, and then also you have a grid here, so you can have let's put the grid here, so you can have different data and then import this to Excel if you wanted or some other application. Okay. Okay, so we can take two more questions here and then conclude here. Okay. So someone asking about your eye diagram were very clean. What kind of noise is added in ordinary optical transmission noises? Additive Gaussian noise, does the same apply to the quantum key? So there is different noises, as I mentioned. In the detector itself, there is shot noise, there is a thermal noise, there is beat noise between the signal and between all of these noises. Also, you have in the channel itself, you're going to have noises coming from, let's say, for example, turbulences or scintillation, so the modulation of refractive index. So there's lots of noise sources. I didn't consider in my simulation all of these type of noises, just to show in the demonstration. But the system is flexible to add up and investigate that. And also you have noise sources addition, as I mentioned to you. There is electrical noise can be added or optical noise can be added into the system and analyze it. Okay, maybe one more question here. Is it possible to simulate micro ring resonator in OptiSystem? Okay, so OptiSystem, as I mentioned, it can talk to OptiSpice software. There is two components in OptiSystem at this moment where you can add up a net list, and this net list can represent a ring resonator or waveguide or whatever the device is, as well as actually in October timeframe, we're gonna release OptiSystem 22. And in OptiSystem 22, we have a new component of OptiSpice, where actually you can design photonic integrated circuit from layout into a component and use it in OptiSystem and do analysis on it. So this is just wait for October timeframe, and then you're gonna see a full demonstration of it. It's really gonna be a good addition to OptiSystem and OptiSpice. Okay, so with this, please let me thank again Ahmed Abu Muswid from CMC Microsystems for joining us, and thank you everyone for joining the webinar. We're gonna look at the questions and then answer them by email to everyone. And if you have again any question, please don't hesitate. My email address is ahmed.atiya@optiwave.com, and you can use support@optiwave.com or info@optiwave.com. Thank you very much and have a good day.
Thank you so much, Ahmed. Thanks.
You are welcome.